today is the 22nd, and I'm ready.
This is from section 4.4, L'Hopital rule.
Okay.
And it is x. Oh, I'm sorry. It should be the limit as x approaches 0. And yep, and then x 5 to the x.
So it's x times 5 to the x?
Correct. And then in the denominator, it is 5 to the x minus 1.
Perfect. Very good. We test to see what situation this is. And 0 times 1, because 5 to 0 is 1, 0 times 1 is 0. 5 to 0 is 1, 1 minus 1 is 0. Lucky case, limit, as x approaches 0. When we differentiate the numerator, please remember this is a product. The first function prime is 1 times 5 to the x plus the first function times 5 to the x prime, which is 5 to the x times natural log 5. How do you remember this? Here it is. We know that e to the x prime is e to the x, and it should be times natural log e. But this is 1. So if we have 5 to the x prime, this is 5 to the x times natural log 5, because it's no longer 1. So therefore,
Yeah, that makes sense, yeah.
so therefore, the denominator now, when I differentiate, I get 5 to the x times natural log 5. Remember the two keywords that you should always have in the back of your mind. Factor is one. Simplify is the other keyword. So then, of course, I see that 5 to the x can be pulled out. And I have 1 plus x natural log 5 divided by 5 to the x natural log 5. Luckily, I can remove this factor. And then when I plug in 0, this is 0, and then I am left with 1 over natural log 5. Any questions?
No, it was the 5 to the x part I was picking up.
Okay, just remember these together.
Mm-hmm.
That basically e to the x prime is e to the x times natural log e. If this is not e, then there is an extra natural log of whatever in there. Good. Anything else? Other questions for me? Anything else? Okay, then I'll dig up my book. And let's start. We continue now with 4.9, which will be part of the last test. So 4.9. Antiderivatives. Antiderivatives. Okay. There are two situations when it comes to notation. Given f of x as a derivative, and given a function f of x. If we are given f prime, and you can say, what's such a big deal? It's just a notation. Yes, but you will see later why. If we're given f prime, we're asked to find f of x. So this is, given this, find f of x. If we are given f of x, we're really asked to find uppercase f of x. Again, what's the big deal? Doesn't really matter. The notation, if it's x or t, doesn't really matter. Okay, so you'll see the notation comes into play a little bit later. Okay, so we are trying now to go backwards. What does that mean? Let's say I'm given a function f of x, which is 2x squared minus 1, and I'm asked to find f prime, which is 4x. This was what we covered so far. This time, I am given 4x as a function, and I'm asked to find f prime of x as the most general antiderivative or I may be given specific conditions or given specific conditions, find the unique, the only one, the unique antiderivative. Okay, let's go back for a second. If I'm given a function and I'm asked to find f prime, you know what I mean. I'm asked to find f of x. So given f prime, which is 4x, I'm going backwards to find the function, and I have two options, depending on what the problem is given to us. Gives us as the most general antiderivative, which you'll see in a moment how, or given specific conditions, find the antiderivative. Before we analyze these two possibilities, I would like to ask you again, when we differentiate x to the n power, we get n, x to n minus 1. I should write times x prime, but that's 1. But now we want to find the antiderivative of x to the n. In other words, which function do I differentiate to get this? So obviously it's a fraction. I increase the power, not decrease like we used to, and I divide by that number. How come that the derivative of this is that? Very simple. Bring down n plus 1 and simplify it, and subtract 1 from the power and get this. So given now this function 4x, let's say given f of x, let's say 4x, find the most general antiderivative. Of 4x. What does this mean, the most general? There are infinitely many functions whose derivative is that. And we're going to write something that works for any real number. So because I'm given f prime, I have to use the notation f of x. I keep 4 unchanged, but I'm going backwards with x to the first power, which means x to the second power over 2 plus a constant c. Now let's see, if I differentiate this, do I get that? Yes. Bring down 2, simplify, get 4x, differentiate c, get 0. But the most general antiderivative means, in this case, is 2x squared plus c. It's a family of functions with all of them have f prime of x, 4x. So when I'm asked to find the most general antiderivative, I'm really asked to find the family of functions whose derivative, all of them, have the same derivative, which in this case, a simple case, is 4x. I would like to practice this concept and then look at the other possibility in which we are given specific conditions to determine the antiderivative. Okay, so I'm looking on page 349. Any of these problems, let's say, let's start with 36. No, I don't want 36 because, sorry, I want to show an example with the most general first, and then the other case. Okay, so let's say, it doesn't matter. Let's start with 4 first. On page 348, and the function is given to us as 8x to the 9th minus 3x to the 6th and plus 12x cubed. The question is asking find the most general antiderivative of the function. Okay. Since we are given f of x, not f prime, I have to use this notation for the antiderivative. Okay, so 8 stays, and I multiply by x, I increase the power by 1, and I divide by the same number. Minus 3, I increase the power by 1, and I divide by the same number. Plus 12, I increase the power by 1, and I divide by the same number, plus a constant c. I will clean it up as much as possible. So f of x, I'll simplify by 2, and I get 4/5 minus 3/7 x to the 7th plus 3 x to the 4th plus a constant c. And now you can say, show me that when you differentiate this function, you get that one. And I will say gladly. So I'm going to differentiate that to show you that we get the starting point. So f prime of x will be 4/5. I bring down 10. I subtract 1 from the power. Minus 3/7. I bring down 7. I subtract 1 from the power. I bring down 4 plus 12. And I subtract 1 from the power. And when I differentiate the constant, I get 0. This is 12 here, sorry about that. So I'll simplify, and I get by 2, so this is 8, x to the 9th. I simplify, I get negative 3x to the 6th. There's nothing I have to do here, and I get that, which is indeed the function we started with. So now imagine what we are doing here. As an example, I'm given the velocity function, and I want to determine the distance function. So far in the course, we were given the distance function, we were asked to find the velocity. Now I'm given the velocity, and I'm asked to find the distance function. I can also be given the second derivative. I can be given the acceleration to find the distance function. First, from the acceleration, I have to find the velocity function. From the velocity function, I have to find the distance function. Any questions on the first example?
I have one.
Please.
When you did the reduction part, you said that you pulled out a 4/5 on all of them, or so when you were proving that? I'm sorry, that.
So when I at this stage when I differentiate.
Yep.
When I differentiate this piece, I bring 10 down and I subtract 1 from the power.
Mm-hmm.
When I differentiate this piece, I bring 7 down and I subtract 1 from the power.
Okay.
When I differentiate this piece, I bring down 4 and I subtract 1 from the power. When I differentiate this, I get 0.
Okay.
So this is the procedure we've been using all the time. The other procedure is the backwards procedure, which we are learning today. So I'm given the velocity function, I'm asked to find the distance function. Here I was just showing you that the function we created, by differentiation, we can check that that is the function we started with. And that's all we did. We just differentiated the uppercase f, the antiderivative. Did I answer your question, Sean? I'm not sure.
Yes, and I also partially realized it as we were going through, like.
Okay. Oh, we're going to have many more examples.
Thank you.
Thank you. So let's choose another from 1 through 22. Please choose. 1 through 22, page 348. We are given f of x, and we are asked to find the antiderivative. This is to be understood that this is a derivative of a function, and we are asked to find basically the family of functions whose derivative will always be that. But this is a function. It's denoted by f of x, but it's a derivative. Okay, I'm ready. Would you like to choose, or you want me to choose?
How about number 17?
17 it is. Any questions? Anyone, please? Anyone? 17, I see it. So f of x is given to us. I'm sorry, it's age of theta. Doesn't matter. 2 sine theta minus secant squared. We are asked to find uppercase f, or uppercase h in this case, of theta. The antiderivative. Two stays. I'm asking myself which function prime is sine theta. And the answer is negative cosine theta. When I differentiate negative cosine theta, when I differentiate cosine theta, I get negative sine. With minus in front, I get sine. Minus. Which function prime is secant squared? Well, that is tangent theta plus a constant c. I will rearrange to remove parentheses, so I have negative 2 cosine theta minus tangent theta plus a constant c. This is a family of functions. All these functions for any c, it can be 0, it can be negative 5, negative 1500. So there are infinitely many functions because this can be any real number. So all this family of functions has the same derivative. 2 sine theta minus secant squared theta. So this is called the most general antiderivative of lowercase h of theta. Do we need another? Or we look at the situation in which there is only one unique answer. The second possibility.
Maybe we could do a rational one for the book?
Yes, of course.
Number
Yes.
13?
Number 13. Whatever the rational... Oh, I see what you mean. I thought you were going to choose like 22. Because I want to show you something about 22. Okay, so we are looking at 13, 1/5 minus 2 over x. Perfect. We're asked to find the most general antiderivative. Which function prime is 1/5? Well, 1/5 x. Which function prime is negative 1 over x? So the negative 2 is says outside. Let me ask this. Which function prime is 1 over x? Anyone remembers? What we differentiate?
Natural log of
Very good.
x.
Yes, but please remember, we talked about this, because the derivative of the natural log of the absolute value will always be 1 over x. So this is the family of functions whose derivative is that. All these functions have the same derivative. There are infinitely many. It's a big family of functions. But now I wanted to point, any questions on this? Is this okay?
Yep, thank you.
Okay, I just want to look at 22 and just put a side note. We do not study antiderivatives of rational functions in Calc 1. You have to wait till the function decomposition in Calc 2. So that's why we can't really use this, because we don't know how to use the function decomposition just yet. So everything that you'll see as a rational function, we have to go around it. So 22 caught my eye because I just wanted to make a point. So in Calc 2, you're going to study techniques of integration. The techniques of integration that we will not study here. The only technique of integration we are going to look at is the substitution rule. Everything else is in Calc 2. So then what do I do with this? So here's what we do with that. So the function is basically x squared plus 2 over x squared plus 1. I am going to divide. You can say divide. Yes. So I'm going to use long division and divide the 2. We can't find an antiderivative of that. Not in this at this level in Calc 1. So x squared times 1 is x squared, so it's 1. We know how to divide. We reviewed in finding the slant asymptote anyway. So x squared times 1 is x squared, so it's 1. 1 times x squared is x squared, subtract. 1 times 1 is 1, subtract. So the function itself can be expressed as 1 quotient plus 1 over the divisor. And this, I know how to find the antiderivative. For that, I don't. There are other options later. I can use a substitution rule on part of it, and we can revisit this at the end of chapter 5. That's substitution rule is the last section of the course. Okay, so now I'm asking myself what function prime is 1. Oh, I know the answer. And now I'm asking myself what function I differentiate to get this. And then I'm going to write plus c. Anyone remembers what we differentiate to get this?
Arctangent?
Excellent. Arctangent